You see them everywhere, right? CPU, RAM, SSD. It's like a giant alphabet soup of technology. But what do all those letters actually mean? Well, today we're going to decode that secret language. We're unlocking your computer.
I mean, really think about it. You push one single button and this whole complex machine just springs to life. I promise you, it's not magic. It's an incredibly fast chain of events, and we're going to follow that chain right from the very beginning.
So here's our game plan. We'll start with how the machine wakes up. Then we'll meet its brain, its thinking core. After that, we'll see where it keeps its data and how that data gets around. Then we'll cover how it talks to the outside world, and finally, we'll dive into the world of software.
All right, first up, waking up the machine. Let's zoom in on that critical moment when a silent, lifeless box transforms into the tool you're ready to use.
Okay, so the second you hit that power button, the PSU or power supply unit sends a jolt of electricity to everything. This wakes up the BIOS, which you can think of as the computer's basic instincts. It immediately runs a pre-flight check called the post to make sure the keyboard, memory, and everything else is plugged in and working. Once it gets the all clear, the modern UFI system takes over to boot up your operating system.
Yeah, see, the old BIOS was kind of clunky. It was all text, pretty slow. UEFI is its modern replacement, and it's a huge upgrade. It's graphical, you can use your mouse in it, it boots way faster, and it has a critical feature called Secure Boot to protect you from nasty viruses before your main system even loads.
Okay, the machine is officially awake. So now, let's meet its thinking core. These are the components doing all the heavy lifting. We're talking about the brain and its super fast, short-term memory.
The best way to understand this is with an analogy. The CPU, the central processing unit, is the chef. It's the one actually reading the recipe and doing all the work. The RAM is the chef's workbench. It holds all the ingredients and tools you're currently using, right there for easy access. And the ROM? That's the permanent printed instruction manual that tells the chef how to turn the kitchen on in the first place.
Now, the biggest difference between RAM and ROM is something called volatility. When you turn the power off, your RAM completely forgets everything. Poof, it's gone. It's a temporary workspace. But ROM is non-volatile. It holds onto its data forever. That's why it's perfect for those critical startup instructions that the computer always needs. So, if we look even deeper inside the CPU's brain, we find the ALU, or Arithmetic Logic Unit. It's basically a super-powered calculator doing all the math. Now, CPUs have two main design philosophies. CISC is like a master chef who can do a very complex multi-step recipe all in one go. RISC, on the other hand, is more like an assembly line where each worker does one simple task incredibly fast. This is why powerful desktop PCs often use CISC, while your super efficient smartphone probably uses RISC.
So we have a brain, and we have a workbench. But where do all your files, your photos, your games actually live? Well, that brings us to data storage, and the highways that data travels on to get around.
For your long-term storage, you've got two main options. The classic HDD, or hard disk drive, is kind of like a tiny record player, with a mechanical arm reading data off a spinning magnetic disk. The modern SSD, or solid-state drive, is more like a digital music player. It uses flash memory chips for instant access to your data. And since it has zero moving parts, it is way faster and more durable.
But, a fast drive is useless without a fast connection. The older SATA cable is like a single-lane country road. It works, but it's a major bottleneck for today's SSDs. That is why we now have NVMe. Think of it as a multi-lane superhighway, built specifically to handle the mind-blowing speeds of modern drives.
All of these parts live on the motherboard, which is basically a giant PCB or printed circuit board. You can imagine it as a city map with tiny electrical roads connecting everything. The fastest road on that map is PCIe. That's the expressway reserved for super high-speed parts like the GPU, or graphics processing unit. The GPU is the dedicated artist that draws everything you see on your screen. And to do its work, it uses its own personal, ultra-fast canvas called VRAM.
There are actually two main kinds of RAM. Your main system memory, that big workbench we talked about, is DRAM. But the CPU is so fast, it keeps a tiny, even faster notepad right next to it. This is called SRAM, and it's used for the CPU's cache. It holds the most frequently used bits of data for instant access, so the CPU doesn't have to waste time going all the way out to the main workbench.
Finally, let's talk about keeping everything safe and running. The PSU, the power supply, is the heart of the computer.
converting the power from your wall outlet into energy the components can actually use. A UPS is basically a life support battery, giving you a few minutes of backup power during an outage so you can save your work. And RAID is a clever way to link multiple hard drives together, either to create an exact mirror of your data for safety or to combine their speed for better performance.
So we have a fully functioning computer. It's powered up, it's thinking, it's storing data, but it's isolated. So for our next step, let's see how it actually talks to the rest of the world.
Getting online is really a little three-step dance. First, your router uses a system called DHCP to automatically give your computer an IP address. You can think of this as its unique street address on the internet. But since nobody can remember a long string of numbers, we use DNS, the domain name system. It's literally the internet's phone book. It translates a simple name you can remember, like google.com, into the IP address that computers actually need to find it.
And while you're browsing the web, you are using HTTP. But if you look up in your address bar and see HTTPS, that S is absolutely crucial. It stands for secure, and it means your connection is encrypted and safe. And what about when different apps need to talk to each other? They often use an API, which is just a set of rules that acts like a universal translator between them.
Okay, we've covered the hardware, we've covered networking. For our final section, let's look at the software. This is the layer that lets us actually do things, interact with, and build applications on these amazing machines.
Most of us talk to our computers using a GUI, a graphical user interface. It's like your car's dashboard, visual, intuitive, full of icons and buttons. But a lot of developers and power users prefer the CLI, the command line interface. This is more like the engine manual. It's all text-based, but it gives you incredibly precise and powerful control through typed commands.
So how does all this software get built? Well, programmers use something called an IDE, which is like a complete carpenter's workshop. It has all the tools they need for coding: an editor, a compiler, a debugger, all in one place. And a popular method they use is OOP, or Object-Oriented Programming. Just think of it like this. You create a detailed blueprint for a house, that's the class, and then you can use that single blueprint to build lots of unique houses, which are the objects. And of course, so much of today's software lives in the cloud. A lot of it is powered by VMs, or virtual machines. It's a wild concept, literally a complete computer running inside another, physical computer. And these cloud services are usually delivered in three main ways. IaaS gives you the raw digital infrastructure, like servers and storage. PaaS gives you a ready-made platform to build your own apps on top of. And SaaS is the finished product, the ready-to-use software like Google Docs or Spotify.
So, there you have it. We've gone on a journey from the power button all the way to the cloud, decoding the language of computing along the way. You now have a much better idea of what's really happening under the hood. So the only question left is, now that you speak the language, what are you going to build with it?